similar processes. So our model can also be used for those purposes. We thank our key collaborator, Bill Wong and SIC, for his valuable inputs and suggestions. Thank you all.
Brian Latimer is next.
All right, so I'm going to talk about how we can integrate biomass into some of the existing or potentially future power generation systems that are primarily using coal. And so my collaborators on this are Jerry Luttrell in mining engineering. He does some work with pelletization, which is a combination of coal and biomass or whatever other kind of materials. He's also done municipal waste. And then also Bingyu Zhao in horticulture, who does genetically modified switchgrass. And so that's another way that we could potentially optimize these types of biomass and select biomass materials that are really catered toward the combustion system that you want to use them. Also, before I begin, the real work is done by graduate students like Gaurav Agarwal, who's in the back of the room, as well as Gang Liu, who is a research associate through the AEP, and so both of those people have been instrumental in helping develop a lot of the data and supporting some of the theory that's been developed in this work. Really what we're trying to do here is develop some new techniques to try and optimize the combustion aspect of utilization of biomass in these power generation systems. So there's a lot of work out there, and it's not a new idea that we want to use biomass instead of coal, but when you look at the literature and trying to select, well, which is the best fuel to use from a combustion perspective, it's really lacking in the types of techniques and methodologies so that you can rank these fuels and make decisions on, for this particular process, this fuel may be better versus this fuel. And so we're trying to fill in that gap by developing methodologies, in particular, how do you rank these fuels? How can you use different combinations of these fuels? If you change fuels, how do you improve their efficiency in one process versus the other process? What are the right parameters to look at to make these decisions? So there's a lot of work out there, but it's pretty anecdotal on, well, I think char yield is the best metric. But there's not a lot of scientific basis when you dig into it from a combustion perspective as to, well, is that really the best use of the total energy of the system? Because we have pyrolysis gases and char that could be potentially available to generate energy in these systems. And so we're really looking at 3 different types of fuel ways in which we can integrate biomass into a power generation system. And by power generation system, as I mentioned earlier, this could be something like an advanced gasification system, or something like our power plant here, where we've got a grate system, and we want to now reduce the amount of coal that we're using in that grate system so that we reduce the carbon footprint of that system. So we're looking at fuels such as biomass, maybe some existing biomass systems. They want to leach out some of the salts that are in those systems to reduce corrosion. So we're looking at the impact of that. Genetically modified biomass, so maybe you want a system that runs completely on biomass, but you want to see, well, how can I make that biomass better? So we're investigating, well, what are the key parameters within a biomass that maybe you should focus on to genetically modify and improve the biomass system. And then lastly, blending coal with some type of biomass or other material for use in these common grate systems. I think that the grate system power plant, although it's outdated, there are a lot of them. And so how do you reduce the carbon footprint of those existing systems? And can we just change some of those materials that we're utilizing in those systems to do that? So the technical approach here is, this is primarily experimental with just a touch of theory to try to help us in the ranking of the fuels. And so to date, we've really focused on quantifying the combustion characteristics of the fuels so that, and developing the data to support our methodology for ranking that I'll go into in a second. Then really doing these experiments on a number of different materials so we can develop and evaluate this ranking system. And then lastly, working with our partners in developing fuel blends or genetically modifying fuels and seeing, well, which of these options are better for different applications. So for fuels, obviously there's a lot of different kinds of biomass, a lot of different kinds of coal, and so we had to really focus down on which kind of fuels we're going to focus on for this seed project. So in this, we're just using one kind of coal, eastern coal, and two different kinds of biomass, switchgrass and corn stover. For the genetically modified biomass, we're just looking at genetically modified switchgrass. So we have a sort of pure biomass that's naturally grown by or pure switchgrass or natural switchgrass, as well as genetically modified switchgrass. And then we're looking at blends of these fuels. For example, I'll just show a little bit on, or comment a little bit on an 80-20 blend, 80% coal, 20% biomass, which is kind of the upper limit, sort of arbitrarily identified upper limit of where you can use biomass in the current grade systems today. And we've also done a little bit on industrial waste like glycerol and municipal waste, plastics and cardboard that you might run into as well. For the experimental side here, what we really want to focus on is try to characterize the fuel through the process that it would experience as it begins to heat up. So you would start with a virgin material. As it heats up, it first starts to generate gases, pyrolysis gases, and this leaves a residual char as well as some virgin material that can still produce pyrolysis gases. If you have an oxygen-containing environment, the oxygen will start to oxidize this char, so you can get char oxidation until you're finally just left with ash. And so what we're trying to do is experimentally control the experimental conditions so we can understand each one of these processes, and then in the end, try to put those pieces back together. We use two different pieces of equipment to do this. One, a STA, it's a simultaneous thermal analyzer, which is a combination DSC, TGA. This is unique in that you can cook things really hot and allow the effluent to come off. You get the DSC signal. It's supposed to be designed so you don't burn up your furnace or corrode your furnace as a DSC, which is always a concern. So this was specifically designed for these kind of applications. The other instrument is a micro-combustion calorimeter that was actually developed about in the last 5 years. The nice thing about this instrument is that you can measure the heat release rate of the gases that are coming off the fuel that you put into here. What is nice about that is you can do that as a function of temperature, and you can relate that back to what you get in a DSC. So now you have an idea of the total energy associated with heating up the material, as well as the energy you're going to get out of the material. And we can do this in controlled environments, zero oxygen, our choice of oxygen concentration. We can do it staged, so we could do, let's understand what's going on in pyrolysis, as well as understand what's going on with char oxidation, and then try to put those two things together to say, okay, if we want to start the fuel off in an oxygen-containing environment, how's it going to evolve during that process, which is the more real process. And then we'll use this data to do the ranking. So I'm going to just talk a little bit about how we do fuel ranking. And what we try to do was define a fuel efficiency. And we did that by first, to define the fuel efficiency, we had what we want out of the system. We want the fuel to produce energy. So that's sort of in the numerator. This is just a kind of basic thermodynamic efficiency. And then in the denominator was what we've got to do to get that out, and what we have to do is we've got to put energy into it. So these are the two things that we've got to measure so that we can define this fuel efficiency. So the first one is the energy required to heat this up, and that just comes out of the DSC. So if we are really careful, and this is not an easy measurement to make, as Gaurav can attest, but this we get the sensible heat, the amount of energy just to heat up the material, as well as the latent heat. And if we do this for pyrolysis, and we just have the heat of decomposition here, then what we want to get out, and this comes from the DSC, as I said, and what we're trying to get out here is the energy produced by these gases, or if we have charring, surface oxidation kind of events as well. So for that, we can get that from the micro-combustion calorimeter. We can get both of those things as a function of temperature, and so then you can define this efficiency as a function of temperature. And the nice thing about that is you can see where different fuels like glycerol, or switchgrass, or polystyrene, or eastern coal, they all will give different high efficiencies, and that occurs at different temperatures. So that's one way that we can then manipulate fuels to maybe generate energy at different points in a cycle. The other way that we can look at this is from a total efficiency point of view, and just by integrating these terms, and that perhaps gives us a little better judge of fuel ranking. And so we get some pretty interesting trends, and I'm running out of time here, but one of the things I just want to point out is the amount of energy. One of the ways that people will look at fuels is how much energy you're going to get out. That does not necessarily correspond with the best fuel, because it may take a lot of energy to heat that fuel up and decompose the fuel. And so we will get a fuel ranking that is counterintuitive relative to the amount of heat you're producing, and also allows us to make more efficient systems. So we have plans to, we've done this for pyrolysis at this point, and we're integrating the char oxidation aspects, and then that should be done within a week, and then we're going to start working on doing some of these genetically modified as well as blended fuels and try to optimize these for different systems, and potentially work in municipal waste. We have published 3 papers relative to this, 1 in a journal and 2 in conferences, and submitted a couple of proposals as well. And I'm going to start working on trying to partner with some of the people that develop pellets and other systems like that to try and see if we can assist them now that we have some tools that I feel like